last few classes you have seen first and second order systems, their time response as well as some characteristics, followed by some Routh-Hurwitz criterion and steady state error conditions. We also discussed type 1, type 2, type 0, all those kind of systems and their implications of like steady state errors and other things. We will continue our review for further, and this particular class we will discuss about root locus analysis. Okay, then we will move on to further topics actually. So if you see the classical control system, this we can summarize it in this block diagram sense. This is a plant here and there is a feedback transfer function which comes into picture. The error signal gets amplified by a gain factor k, which essentially serves as a controller here. And if you see the closed loop system, the effective transfer function is dictated by this. So, this is a reference input to output. The closed loop transfer function is dictated by that. Okay. So, that is essentially k times g of s into h of s divided by 1 plus k times g of s h of s, provided there is a negative feedback. If it is a positive feedback, then you will have a minus sign over here. There is a fundamental problem here as far as poles 0 consideration. We are primarily interested in poles and zeros of transfer function, because we have seen that the stability characteristics are largely dictated by pole locations. However, there is a fundamental problem here, because poles of open loop transfer function are rather easy to find, and open loop means we mean this k into g of s h of s, that is the open loop transfer function. It is rather easy because g of s and h of s once we know, and typically they are given in fractional decomposition sort of form, s minus a into s minus b sort of things. Once you do that, it is rather easy to find that the poles and zeros location. However, if we talk about closed loop poles, which are of our primary concern, then we have to do this further algebra, and that is dictated by the poles or the roots of this particular polynomial, which will appear here in the denominator. Okay. So, if possible, we want to avoid this complicated algebra and quickly want to infer some stability characteristics of this closed loop behavior from the open loop pole location. The question is it possible? Okay. Is it feasible? And the answer turns out to be yes, it is feasible, and that leads us to this idea of root locus analysis actually. Okay. And one more thing to notice, these pole locations of the closed loop transfer function are also functions of the gain. Okay. However, the open loop pole locations are typically not functions of the gain. They are functions of the gain in a if you equate this equation to 0, then it essentially whatever solution pops up is actually a function of gain k. However, here if you make it equal to 0, then the k cancels out. So, typically it is not a function of gain basically. So, that is another advantage actually. Alright. So, example sense, let us see, let us take g of s like that, h of s like that, and then k times g of s, h of s becomes simply like that, just multiplication of these two transfer functions. And hence, the open loop transfer function poles will be at 0, s equal to 0, s equal to minus 2 and s equal to minus 4. So, these are open loop transfer function poles actually. However, the closed loop transfer function is dictated by something like this. Okay. So, what happens, we can clearly infer that poles of these closed loop transfer functions are not immediately known. Once we know the value of k, then only we can solve this and find out that particular location for that particular gain k. And then system stability and transient response, however, depends on pole of this one, not pole of that open loop thing. Okay. So, that is another thing. So, root locus essentially gives a vivid picture of the poles of T of s as k varies. So, one particular value of k will not be interested, we will take all possible values of k, and typically when we talk about negative feedback system, we talk gains as positive constants. So, it varies from 0 to infinity typically. So, as gain varies, then where do this pole go? Where do they start, where do they go, things like that actually, that is our concern. So, before proceeding further, we can see this vector representation of complex numbers and complex functions. So, if you talk about a simple complex number, okay, which is s equal to sigma plus j omega, then in a s plane we can you can have the real component sigma and j omega is the imaginary component actually. And if you simply take f of s, which is a function s plus a, then a being a real number, then essentially the real component gets changed, sigma plus a it becomes, imaginary part remains same. So, essentially you can also give it another vector representation with real part sigma plus a, imaginary part just omega. As an alternate representation, however, you can change this origin to the 0 location. Okay. So, let us not start this vector from origin of this particular complex plane, we will start this vector with minus a. Okay. Then it will terminate at j omega only. Okay. So, we can either you represent it by this vector or you represent it by that vector. Okay. So, as an example, if you take s plus 7, okay, as at s equal to like 5 plus j2, then it starts at minus 7, okay, and then ends at 5 and j2. So, it is essentially how you represent, how you visualize this vector diagram essentially. Okay. So, we can conclude that s plus a is a complex number and it can be represented by a vector drawn from the 0 of the function, which is minus a, okay, to the point s. That is the alternate representation essentially. So, how does it help? Now, if you in general we just took a, here we took a very simple function. Now, in general we are interested in transfer functions, which is a numerator polynomial by a denominator polynomial. So, in general we will be able to represent it something like this. So, it is a multiplication of terms in the numerator s plus zi, that is s plus z1, s plus z2 like that, up to m, s plus zm, and then denominator polynomial s plus p1, s plus p2 and things like that. The z stands for 0 and p stands for pole typically, that is why these constants are used here. And then the magnitude of this particular value, that f of s, actually if you just compute this m magnitude, then it turns out to be multiplication of magnitudes of this divided by magnitudes of that by complex number theory basically. Okay. So, magnitude is rather easy. The angles, when you try to find angle theta of f of s at any point, is given by angles emanated from this, like angles that comes out from this minus the angles that comes out from there. Okay. That is this simple complex number theory actually. So, what you tell the magnitude of this particular function is dictated by this formula, whereas the angle that comes along with this f of s is dictated by this subtraction formula basically. Okay. Example again, if we take a function s plus 1 by s into s plus 2. So, this particular if you see this vector originating at minus 1, see there is a 0 here at minus 1, there is a pole at 0 and there is a pole at minus 2. Okay. So, if you take let us say one particular point we consider, okay, and probably like minus 3 plus j4, that is the point that we are considering. Okay. And then what you are telling here is this various vectors have their magnitude as well as angles. So, the magnitude for this particular vector which starts from minus 1 goes all the way is given like this, square root of 20. Angle means it makes angle from positive to this particular angle, okay, in anti-clockwise sense. And then a vector originating at 0, that is given by that, okay, 5 angle 126.9. Vector originating at minus 2 is again given by something like that. So, this information we know basically as far as this particular point is concerned. Now, the question is like what is the angle of what is the magnitude and angle associated with this particular function evaluated at this point. Okay, this is a function s plus 1 divided by s into s plus 2, that needs to be evaluated at this particular point s equal to minus 3 plus j4. So, then this will go to a different point and that point is dictated by what magnitude and what angle actually, that is what our concern. So, then using this previous formula what we have here, the magnitude turns out to be like square root of 20, because that is a 0 divided by this magnitude 5 into magnitude square root of 17. So, that is the magnitude part of it, and then angle is angle of 0, okay, first positive, you have to sum it up, all zeros angles you have to sum it up. So, there is only one 0 out here. So, that is the part minus the angles going from poles actually. So, these are the two poles and the minus 126.9 minus 104.0, and if you simply do this algebra, it turns out to be this is the vector that we are talking here. So, if you just take this point, pass it through this function, it will turn out somewhere like 0.217. So, that means somewhere here. Okay. So, it will turn out to be something like 0.217, that is the magnitude going from here on whatever direction, okay, starting from this origin, that is the magnitude with 10 minus 114.3, that is what it is. So, it will turn out to be in the somewhere in this direction actually, probably you can verify that maybe. Okay. So, that with this concept we are kind of ready for root locus analysis, just to see a brief overview of what it talks about actually. Some of the facts, first it was introduced in 1948, almost after the Second World War. So, the design that has gone into this First and Second World War is probably not took help of root locus analysis. They were essentially based on frequency domain analysis, which we will see maybe next class, some of that. And then it is introduced around 1948, and then there is a graphical representation. Root locus essentially talks about some sort of a graph of the closed loop poles in the S-plane as the system parameter varies. That means, the system parameter essentially what we mean is the controller gain actually. Okay. So, as we vary the controller gain from 0 to infinity in that particular setup what I discussed. So, this particular thing I told that if it is a negative feedback, k varies from 0 to infinity. Then as k varies from 0 to infinity, where do these poles go actually? So, that will give us some sort of a locus, that means some sort of a graph which we are interested in actually. Okay. So, and then essentially it also contains qualitative as well as quantitative information. So, it is just not only qualitative, it also talks about precise quantitative information as well actually. That means, if you are if you just freeze your attention to one particular point on the root locus, it actually gives you that particular pole location for that particular value of gain k. That also has a quantitative information. And the beauty of this particular method is also it actually holds good for higher order systems. See, most of the analysis what we know in classical control systems are typically limited to second order or second order approximation, things like that. This is not limited to that. It can it still talks about this higher order polynomials to an arbitrary degree basically. You can take it to very high order. Anyways, here we will discuss a small example again. This is a practical example taken from again Norman Nice. So, what it talks about is some sort of a camera control system, and this camera is capable of tracking an object. The moment you point out an object here, then it will keep on tracking that under its limitations actually. And so, this obviously has a motor, okay, and then that motor is supposed to tilt this camera up and down sort of thing actually. Okay. In that particular plane, it is capable of tracking. So, this essentially this system's input and output is given by this kind of a transfer function, which is a motor camera transfer function k2. Typically, we do not have a control on the value of k2 per se, okay. But sometimes it may allow us also. That is not our primary concern here. It also has an amplifier which serves as a controller gain k1, which essentially we can manipulate. So, then if you see this closed loop transfer function, unity feedback gain sort of thing, unity feedback system, essentially it turns out to be something like that, where k is nothing but k1 into k2. That means, if you manipulate k1, then the gain of this particular system closed loop pole are also affected through this gain k. Okay. So, now what we do, we go back and okay, we will vary this gain k. Now onwards we will not talk in terms of k1 and k2. We will dump everything in terms of k basically. So, we will vary this gain from k equal to 0 to very high value, let us say. In this particular case 0, 5, 10 of step 5 basically. So, take 0, then 5, then 10, 15 like that, and then compute these roots of this polynomial. Now, once you fix a value for this, then the roots are available anyway. For example, if you put k equal to 0, then this is like s square plus 10s equal to 0 here. Okay. So, essentially it gives us s equal to 0 or s equal to minus 10. So, that is s equal to 0 or s equal to minus 10 here, like that. So, the moment you put some value 5, then you again go back to this quadratic formula, that minus b plus or minus square root of b square minus 4ac divided by 2a. That will give you 2 poles actually. So, that way you will compute, keep on computing actually. So, then we will list this, generate this table and then tell, okay, this k varies from 0 to 50, let us say, then pole 1 will be of this order, I mean this way it pops up, and then pole 2 pops up this way. Okay. And what we observe at first cut, that this particular set of values, okay, if you see the first part of it, up to k equal to 25, okay, the poles were all real, okay, there is no imaginary component. That means, this is actually up to k equal to 25, 0 25, this system behaves as if like a overdamped system. Remember, this is all second order system here, okay, and by design it is also like a stable system sort of thing. Okay. So, we are interested in for observing some properties here, and then that is when first observation is when until k equal to 25, the system behaves as if it is a overdamped system. After that, it starts behaving as if it is an underdamped system. Okay. Now, further things. Okay. So, poles, as you vary these gains from 0 to 50, the poles what you see here, one pole is at origin, but after that they are all negative side, right, all negative real parts actually what you see here. So, that is what it pops up here, that is I have just located these locations of the poles in the complex plane, and then as k varies, the poles are always in the negative side, that means the system is always stable. Okay. And then further observations, the poles will start from like that. If you see this table, it is 0 minus 10, then minus 9.47, 0 minus 0.53 like that. So, the one pole starts here, one pole starts here, then it starts moving this way, this starts moving that way, and then at this point of time one goes that way, one goes this way actually. Okay. So, what happens actually? So, once it starts going this way vertically, once it really becomes a complex number, it actually becomes a complex conjugate pair. That is a property we know. For real physical systems, the coefficients have to be real, and the coefficients are real means the roots have to be complex conjugate actually. Okay. So, once it starts doing that way, okay, what does it tell actually? Because this real part remains same. Okay, once the real part remains same, because settling time is roughly 4 by zeta omega n, right, and this component is kind of zeta omega n component actually, we know that. So, as long as this component remains same, the settling time remains same, no matter what gain you select after that. Whatever gain you select after that, the settling time will remain same actually. Now, as the gain increases, that is where the poles will travel, one going up and up, one going down and down. What happens actually? So, we observe that this angle keeps on going up more and more high actually. Once the angle, this theta component, what means if I draw any particular location, if I draw some sort of a line here, sorry, this is a straight line supposed to be, okay, this is a straight line, and then the next one it is supposed to be one more straight line. So, this travelling is through this actually, like this happens this way. Okay. So, as the angle keeps on increasing, we know that zeta, that the damping ratio is a factor of this cos theta component, this is the theta part of it. Then it happens to like when theta increases more and more, then cos theta decreases. So, that means the damping ratio starts decreasing actually. Okay. Okay. So, the damping ratio starts decreasing actually. And for the same time, the percentage overshoot starts increasing also, because the pole locations go that way. So, essentially what we have done, we started varying this gain k, then we started plotting these values, and then we joined these points that came across, and then it gave us a lot of qualitative information actually. And if I really freeze one particular value of gain, then I have a particular value of these poles, and hence it will give me exact values of settling time, exact values of damping ratio and things like that. So, it also gives a quantitative information as well actually. Okay. So, this is the motivating example, and let us study further formalizing these concepts actually. So, now we are ready for discussing some of these properties of root locus actually, in a generic sense. Okay. So, we start with this this closed loop system, this is the closed loop system dynamics, and this is the closed loop transfer function. Okay. And hence the characteristic equation, when you see this is given by this particular equation is equal to 0 that way. Okay. So, if I really all that I have to do is analyze this equation slightly carefully actually. This is the characteristic equation what it comes up for closed loop system. I have to analyze it a little more carefully actually. Okay. But in general this particular equation I can represent this, I can interpret this rather as a complex equation sort of thing. Okay. Because this g of s and h of s, where s is actually s varies in a complex plane. So, this entire equation is a complex equation sort of thing, and hence this equation has to be satisfied. What you see here, okay, this is the primary equation that we are talking actually. So, k into g of s into h of s should be equal to -1 in complex sense actually. So, what does that mean? This -1 embeds two information, that the magnitude has to be 1, okay, that the magnitude has to be 1, and the angle of -1 is an odd integer multiple of 180 degrees actually. Okay. So, if my s, that particular value of s is actually part of the root locus, then that particular value, if I just draw a vector diagram, then the magnitude has to be 1, and then the angle has to be this odd multiple of this 180 degrees actually. So, these row conditions are called Evans conditions, and you can formally write it as one, first is a magnitude condition, okay, and the second is angle condition, angle criterion actually. Because these two essentially dictates the root locus behavior and plotting the root locus. How do you do all these things hover around these two conditions essentially. Again, before proceeding further, let us see a small example here. Now, we know that this angle condition actually plays a little pivotal role or primary role in deciding whether this is part of the root locus or not actually, one particular value of s. So, let us see that, and then if it is a part of the value, if it is really part of the root locus, then the gain is actually dictated by this formula, okay, because gain we are interpreting all through we are interpreting gain as positive value. So, this positive value comes out of here, and you are left out with 1 by this formula actually. First thing, the angle condition helps us to know whether it is really part of the locus, and if it is part of the locus, then the magnitude is given, magnitude of that gain value, what is the gain value that corresponds to that particular value of s is given by this formula actually. Okay. So, let us consider this transfer function. Remember, this is the open loop part of it, h of s is equal to 1 here. So, this is all that open loop transfer function what you have here. So, we are considering 2 points P1 and P2, okay, and remember these are the open loop zeros and poles here, and later we will also utilize this particular example to draw a root locus formally. Okay. So, this P1 and P2 let us analyze a little more, and then let us talk about P1 per se. Okay. Then P1, going back to the same formula what we talked about angles and all, the two angles are coming from zeros, this theta 1 and theta 2, and two angles are coming from poles, theta 3 and theta 4. So, if we compute these angles theta 1, theta 2, theta 3, theta 4 and carry out the algebra, then it turns out this is the angle which is not an integer multiple of 180 degree. So, obviously, this point P1 what you are talking here is certainly not a part of the root locus actually. Okay. However, if you talk about a point P2, this point is like this -2 plus j 1 by root 2 essentially, that particular point. If you do the same algebra again, it will turn out that it is the summation of these angles is actually 180 degree. That means, point P2 is actually part of the locus, and once it is part of the locus, what is the gain value for that particular value which corresponds to this particular point is given by this formula. So, that is L3 L4 divided by L1 L2, and you carry out this magnitude condition, this is given by this, that is what you are using here, and it turns out that the magnitude is something like that actually 0.33. Okay. So, what is the summary? The summary of this observation is, given the poles and zeros of an open loop transfer function, a point in the S plane is on the root locus for a particular value of gain k if the angles of the zeros minus the angles of the poles add up to an odd multiple of 180 degree. Again, this is a repetition of what we have already studied just now. And furthermore, the gain k at that particular point can be found by dividing the product of the lengths of the poles divided by the products of the lengths of the zeros. Okay. Remember, it is not lengths of the zeros by length of the poles, it is length of the poles divided by length of the zeros, the gain, because of the 1 over 1 by this factor comes in actually, that is why. Okay. Alright. Now, formally stating how do you sketch a root locus, and remember there are some basic 5 rules and further rules are also available for smoothing and all that. Essentially these rules were the root locus were developed when the computer were not there, computer power was not there, and that is actually the whole idea of classical control system in a way. The classical control system talks about transfer function, and the transfer functions was a necessity to avoid differential equations as it is actually, and the large handicap at that point of time was unavailability of computers, which are very obvious nowadays actually everywhere. So, one idea was without solving this all the values of gain k, we cannot keep this particular example that we studied was a second order system, and we know the root how to solve the second order polynomial, because the closed form formulas are available. So, rather we can do it not in a it is not that difficult to carry out this algebra that we discussed. The moment it becomes higher order things, higher order polynomial, getting the closed loop solutions that way is not that easy actually. Okay. So, and that is not a very straightforward manner, we cannot get the values by pen and paper calculation. However, we want to sketch the root locus actually. We need to have an idea of how that locus appears in the complex plane. So, there are some beautiful results there, and some 5 rules. So, let us study. First thing is number of branches, how many branches a root locus can have, and this is very obvious because root locus by definition is the locus of the roots. Okay, roots mean locus of the poles. So, the number of poles is number of the branches, right. So, if you have the number of poles, okay, dictate how many branches of the root locus are there. Okay, that's rather easy to see that actually. Now, symmetricity rule, okay, a root locus is always symmetric about the real axis, because the complex pole must always appear in conjugate pairs actually. Okay, if there is a complex part, then it should appear in the conjugate pair, otherwise it is not good, the transfer function is not good for a physical system. So, that is the problem actually. If it is valid for a physical system, then the coefficients of the polynomials are always real, and for that, in those class of polynomials, the roots must be conjugate pairs, and either it travels in the on the real axis, or it appears as conjugate pairs. So, obviously, the root locus is always symmetric about the real axis. Okay, that is also not difficult to see. Now, here is a critical observation. Okay, and this observation tells us that the real axis segment, if you just consider the real axis of the complex plane, in which segment the root locus appears on the real axis, that is the question actually. Okay. Now, it turns out that if I just analyze any point P1, let us say, okay. So, these are all open loop pole zero locations, let us say. Okay. Now, let us assume that these 2 zeros are appearing here and 2 poles are appearing here. Now, if I simply consider the angle between these guys, okay, these angles that is coming to this actually, the contribution of the angles from these 2 poles will cancel out, and the contribution of the angles of the 2 zeros will also cancel out actually. Okay. So, what happens essentially? So, they really do not contribute any as far as the angles are concerned actually. We know that if it is a part of the root locus, then this must satisfy the angle condition somewhere actually. Okay. So, for the angle condition, these poles and zeros do not play any role actually. Okay. So, what is it left out? We are left out with only poles and zeros that are appearing on the real axis basically. Okay. Now, we know that if there is a pole, if there are 2 poles, let us say I consider a pole somewhere here, then there are 2 poles here, okay. Then these 2 poles will contribute to even multiple of 180 degree, right. If I consider these angles as 180 degree, then it will turn out to be even multiple, and hence they are not part of the root locus anyway. We always want odd multiples actually. Okay. So, what it essentially tells us that on the real axis, for gain k positive, greater than 0, the root locus always exists to the left of an odd number, Okay, because any pole and 0 that appears to the left of this particular point P1 will always contribute an angle 0 basically. So, that is also not a candidate for odd multiples of 180. It is always 0. If I consider this particular pole, the angle to that is kind of 0, and this angle to that is also 0, like that actually. So, I will not consider that part of it actually. So, all that I am left out is poles and zeros to the right of that particular point. So, essentially what it means, the root locus exists to the left of an odd number of real axis finite open loop poles and zeros actually. So, if I just consider these poles and zeros on the real axis and I start counting from the right, okay, there is one pole here. So, that is an odd multiple of that is an odd integer. So, there should be some root locus here, but once I come this segment, there are 2 poles here. So, there should not be any root locus here. Once I come here, again there are 3 poles. So, there will be root locus in this segment, like that actually. You can continue doing that. So, that will give us some idea of which segment of the real axis my root locus lies actually. Okay. Now, the number 4, let us see what is it, starting and ending points, where does the root locus starts and where does it end actually. And obviously, the root locus begins at finite and infinite poles of this, and it ends at finite and infinite zeros of open loop, open loop zeros actually. So, the root locus essentially starts at the poles of the open loop transfer function, and it ends at zeros of the open loop transfer function. It is easy to analyze also, like if you just take the closed loop transfer function and then carry out the algebra in the limiting sense, that what happens when k tends to 0 and what happens when k tends to infinity, then these results pops up actually. Details are there in the book actually, you can see that. And then so suppose there is a pole, equal number of poles and equal number of zeros, then the matter is okay, because it will start from a pole and at a 0. So, that is there. But most of the time what happens is the number of zeros are typically lesser than number of poles, and in those sense the one of the ideas in classical control is for any pole 0 deficiency, those can be assumed to lie at infinity. Formally it can be shown also that they can lie in the infinity actually. So, any root locus that does not end at a finite 0, it actually ends at an infinite 0. So, that is there actually. Now, if it really ends at infinite 0 on an S-plane, in which direction it will go actually? The S-plane is all over actually, right? Any angle it can go to infinity, right. So, then the question is then this rule number 5 comes into picture, that tells us the behavior at infinity. Okay. So, the root locus approaches to straight line as asymptotes at the root locus approaches to infinity. So, let us conceptually let us see this. Suppose this is something like that, and the root locus where it will go to infinity, in all direction it tends to be, which direction it will go. So, now it turns out that if you use this formula what is given here, okay, with this particular value of sigma a and this particular value of theta a, I can draw some sort of asymptote actually. Okay. And any pole that starts from somewhere here and there is nowhere to go, then it will actually do something, but eventually it will go towards that asymptote actually, it will merge on that asymptote basically as k goes to infinity. Okay. That is the whole idea basically. Okay. Remember, this is the sigma a that we are talking here, okay, is not the y axis intercept, it is x axis intercept. So, this is the part that we are talking here, that is the x axis intercept actually. Okay. And the angle is that particular angle. Okay. So, these are the basic 5 rules. Other rules do exist, other rules something like they give us ideas of the y intercept, like the imaginary axis intercept, where it will intercept on the imaginary axis, that will come from the Routh-Hurwitz criterion. Then it will also tell us, there is one more rule which tells us on the real axis at which point it will start going to the complex domain, that is the point of departure actually. So, that also is available. Then some of these rules are actually there in this book, this particular book, you can study that actually. Okay. Well, this is in the review class, I will not talk too much details on those actually, but let us using these 5 rules, let us study that particular small example that we discussed here before. So, this is the system that I am talking here, and these are the 2 poles and these are the 2 zeros of this open loop transfer function. So, let us go back to rule number 1, number of branches obviously equal to the number of poles, which is 2. So, there must be 2 branches. It has to be symmetric about the real axis. So, these 2 are there. Now, Now let us talk about rule number 3, real axis segment. Which segment it will appear? Obviously, there is one pole here, so this is a odd multiple. So the root locus should appear in this segment, and then 1, 2, 3. So this root locus should appear in this segment as well on the real axis, as far as real axis is concerned actually. So it should one part should start from here, one part should start from here, and both the things, one should end here and one should end here. Okay. And then this part of the real line I should have a root locus, and this part of the real line I should also have a root locus actually. That the rule number 3 says. And starting and ending point we already covered, that we should start from a pole and end at a 0. Okay. And using this, and the further conditions are there, as I told, that the point of departure and point of arrival can also be can also be computed from some derivative conditions actually. So essentially we know that one thing should start here, one thing should start here. These points of departure and arrivals are known, and where it will go ultimately, that is also known, and it has to be symmetric about the real axis. So all these condition gives us an idea that the root locus should behave something like that. One part, I don't know which part goes where, that part is kind of, that information is silent, but you can assume that this segment, this part probably starts from here, it goes, and then it goes here and it goes there, and this part starts from here and it goes through that and it goes there. Okay, so that's the kind of representation of root locus actually. Further details are there in the book, you can see it actually. Now after we plot the root locus, we should take advantage of that, okay, to the best extent possible actually. And how do you really, it actually helps us in tuning the gains in a good way basically. Now there are some ideas that in classical control, that if there is a higher order system, you can roughly interpret that as a dominant second order poles, dominant second order systems, and you can keep only the dominant poles. Then you know the settling time formulas and all that actually, assuming that there is no zeros in the loop, and then assuming that there are only 2 dominant poles actually. For that particular approximation, you know this settling time characteristics and then percentage overshoot, things like that actually. So you can use those things and tell, okay, if my system is largely like a second order system, then that should be my damping ratio, let's say. Then this will give you some angle, that is the cos theta is that. So theta will be, you will know that. So you draw a line, and wherever it intersects this line with the root locus, let's say you pick up that particular pole actually. Okay. So that particular location on the root locus will correspond to certain value of gain k. We know that. As each of the location corresponds to a particular value of gain. So I will select that particular value of gain. Okay. So that will, then I will go back and simulate the original system actually. Okay. So to some extent it gives us some sort of a design procedure of selecting the controller gain k actually. Okay. Now that may or may not be sufficient though, because if it is sufficient, I am done. But if it is not sufficient, that means, remember that gain variation can only allow me to select poles on the root locus. Anything other than that is not feasible. Okay. But really, if I want some other location, let us say location B here for different correct, this angle remaining same means damping ratio will remain same, but that is not everything. Let me see that, okay, for example, these 2 points will correspond to different settling time. And so let us say this settling time is really good. Okay, looking at this plot also it is very clear. This pole at A will give large settling time, which I probably want to avoid. So I will go for this particular pole location, which is the same damping basically. That means it will have same percentage overshoot, but it will have a better settling time characteristics also. Okay. Then only root locus, plotting only the root locus will not help us actually. We need dynamic compensators. That means we really need some sort of a integral loop or derivative loop, which essentially leads us to see what we have so far is only proportional gain k constant. So that p loop is already there in this part of it, but in addition we should also have some sort of a integral loop I or derivative loop d. So that essentially leads us to PID control design actually. Okay. So if any pole on the root locus is fine with us, then a simple gain adjustment will do, otherwise we will go for PID design. So let us see an overview of the PID design, and we will see probably little more detail next class also actually. So essentially what is PID design? PID controller, okay, essentially has 3 blocks, okay, in the loop, and we already had this P loop so far in the discussion actually. Okay. In addition, we are talking about a I loop, which is integral loop, integral feedback, and there is a D loop, which is derivative feedback actually. And it essentially turns out that if I manipulate this error signal, which keeps on coming to me in a time history sense, then probably I will have a better characteristics of the closed loop process actually. Instead of simply instantaneously adjusting the error signal, I will also take care of the history of the signal, or I will also try to predict the error signal little later actually. So, that means the derivative information gives us an idea of what the error signal should be in the future. Okay. So, if I manipulate these characteristics, then I will have a better property actually there. So, what essentially turns out, this will have 3 gains, one is the proportional gain, one is the integral gain, one is derivative gain, and by manipulating these 3 gains, okay, I will essentially synthesize a controller as a summation of all these 3 signals actually. Okay. So, by tuning these 3 components or gains, a suitable control actions is generated that leads to desirable closed loop properties actually. Okay. So, you are not handicapped by only this P part, you are having a much more powerful tool by bringing in the D and I component actually. And in transfer function sense, we can represent this way. Okay. Earlier we had only this this part of it, okay, K1 part of it. Now we are talking about both K3 as well as K2. Remember, this is an integral part and this is a derivative part actually. All right. So, what is the philosophy? Let us say what these different components do actually, what are they capable of doing. The proportional component determines the reaction to the current event of the output error. So, it is ignorant about the history, neither history nor future. It just talks about the current value of error and tries to kind of minimize that actually. So, it essentially serves as some sort of a all pass block. It does not contain any frequency chopping property basically. Just whatever error comes, it just manipulates that error and then gives a control signal actually. Now, integral component determines the reaction based on the integral or sum of the recent errors actually. So, integral, what we are talking here is finite time integral. So, we will have some finite length of integration. Okay. So, that particular value is multiplied by a gain Ki, okay, then it is used as a control signal actually. So, in a way it accounts for the history of the error and essentially serves as some sort of a low pass block actually, because high frequency component, we know that if there is a signal, okay, the integral value will vary very slowly actually. Okay. Even if the, let us say if you talk about some signal, okay, which is like that, if you talk about integral value, integral starts at 0 obviously at time 0, okay, okay, then it will not have that variation actually, it will have low frequency variation. Okay. So, we will essentially can interpret this as some sort of a low pass block actually, okay, for the integral component part of it. The derivative, however, is actually fast reacting and it actually takes care of the, it manipulates the rate of change of the error actually. So, in a way it accounts for some future value of the error, because if you use this Euler integration formula, then essentially it tells us that E k plus 1 is actually E k plus delta t into E dot k, and this E dot k is the derivative component part of it actually. So, by knowing this current value and this derivative component, I can actually predict what will happen to my error k plus 1 in a rough way basically. So, I am using this property ahead of time actually sort of. So, essentially it accounts for some sort of a future value of error and serves as a high pass block actually. So, proportional is a all pass block, integral is some sort of a low pass block, and derivative is some sort of a high pass block actually. Okay. So, in time domain we interpret this way, this is the error signal what it comes. So, this control signal is partly from the proportional part, then the integral part and then the derivative part. Any combination of that we are free to use, by the way. We do not, we not necessarily have to use all the gains all the time. In some part of the gain we can take it as 0 and then may not use it also. That depends on the particular application and what we want to do really actually. So, in Laplace variable sense, it the same thing can be represented something like this actually. Okay. So, the tuning parameters are something like proportional gain, and then the integral gain, and there is a derivative gain. And these these integral and derivative gains are always compared to proportional gain, whatever proportional gain what you have, how much scaling you are doing actually, that essentially plays a role. And hence this integral gain I can write it something like this, divided by some constant T I, and the proportional derivative gain I something like I multiply by some constant T D actually. Okay. Okay. Then effects, let us talk about a little bit elaborate sense. The proportional term is essentially coming out to be something like this, Kp into Et, right, that is the proportional term. So, essentially in this proportional term what we are having is Kp was the proportional gain actually. Okay. So, if the gain Kp is low, okay, then this component turns out to be very low, and it may not be sufficient for our need actually. It may not give us the desirable settling time properties actually. It will have a large settling and things like that, which we may not require. And on the other hand, if it is very high, then essentially it has a property of making the overall system unstable. There is a high gain drawbacks actually. Okay. So, we really do not want this Kp to be very high either actually. Okay. And the moment Kp is very high, remember this all pass filter, all pass block sort of thing. So, any noise component will also get amplified by this y value of Kp, and it will affect the system dynamics. Okay. So, that is also not desirable actually. So, just select this Kp judiciously sort of thing. Now, coming to the integral term. So, this is the loop. So, this is the component that we are talking here. Okay. And as here the Ki is essentially the tuning parameter. Okay. So, the integral term when added to the proportional term, actually it helps us in accelerating the movement of the process towards the set point. Okay. And because there is a extra enforcement, you can think of that way. Okay. Even though Ki value is constant, this integral term is supposed to build up actually, right. As long as, suppose even if you talk about some sort of a bias value, let us say steady state error sort of thing. Okay. So, let us say this is that, and we know that this is a second order system and there is a steady state value. And if you really start your integral block somewhere here, then you know this integral area under the curve keeps on building actually. So, even though this gain value Ki is a constant value, okay, this area term keeps on building, and hence this component keeps on building up actually. Okay. So, that essentially helps us in eliminating the error in a good way. And we have seen in the steady state error analysis also that if you have a integral in the loop, then essentially it gives us some sort of a additional, it makes the type 0 system type 1 and type 1 system type 2 like that, because of this divided by S property. Okay. So, any finite value of error that pops up in type 0 system, let us say, suddenly the type it becomes a type 1 system, and hence the steady state error becomes 0 actually. It helps in eliminating the steady state error basically. Okay, these are the good things, but what the bad thing? The integral loop should always be used in a judicious manner, because of there are certain bad things actually. First thing is there is some sort of a destabilizing effect of the integral term, and probably we will understand little more when we know about gain margin, phase margin, things like that in a frequency domain analysis. Now, if you assume that for a second that you know that, then it turns out that the magnitude part is given by something like this, which is 1 plus there is some component here. Okay. Right. So, essentially what it does, if you talk about this sort of a tuning here, okay, something like that, it essentially comes up with something like this, and hence this is invariably a number which is greater than 1. Okay, right. So, this gain is the overall gain of this proportional controller, you can interpret that there is a gain multiplication factor actually, okay, which is greater than 1. Okay. That means the gain becomes more and more, that means the gain margin becomes less and less actually. Okay. So, essentially you can see that in a little elaborate sense, something like this. Let us say the root locus is something, it goes like that, it comes like that, and it goes like that way. So, there is a gain value after which the system goes unstable actually. Now, as gain increases, the root locus travel like that. Okay. That means, if you go more and more close towards this value, you are approaching more and more instability region actually. Okay. You are becoming closer and closer towards the unstable domain. So, so essentially this pushes you towards that kind of towards that side basically. Okay. So, the gain margin becomes lesser and lesser. Margin is the value that is left out before the system becomes unstable actually. Okay. So, if the gain value keeps on increasing more and more, the margin becomes less and less actually. And for the phase angle characteristics also, it essentially gives us something like this, and we know that tan inverse of a negative quantity is also a negative quantity. Okay. So, essentially it actually it increases the phase lag also basically. This is a lag factor. Any negative value is a lag factor. So, essentially it increases the lag factor also actually. So, that means what happens? It essentially leads us to the reduction of gain margin and phase margin both. Okay, that means you are essentially compromising on robustness characteristics a bit actually. Okay, so, that is you have to be slightly careful about that. There is a larger problem of what is called as integrator wind-up. That means, if there is something like the control action is saturated, and that saturation even after it saturates, you keep on evaluating this integral term, then the evaluated term becomes more and more and more and more large and large, because the error never dies, the error never goes to 0. The integral term actually stabilizes once the error becomes 0. After that, there is no integral component actually, but if it does not stabilize, the integral component keeps on building actually. Okay. So, then it essentially keeps on predicting more and more and more and more. So, you will never be able to come out of the saturation actually. That is a larger problem which is called integrator wind-up. The remedies for that is the periodic resetting of the integral value, because see this particular term, the 0, what it starts from 0, you start from t0 rather, and keep on resetting the t0. Okay. So, this integral value starts again from t0 to t0, that means again it becomes 0 actually. Okay. The integral components periodically set to 0 basically. Okay. Then it again, that is one remedy, and there are explicit anti wind-up logics also. People have devoted a lot of attention to this particular problem, even on nonlinear system, that is a problem. So, there are anti wind-up logics available in an explicit manner actually. Now, coming to the last term, derivative term, what does it do? The derivative term actually helps us speeding up the transient behavior. Okay, because we are talking about accounting for future values of the error in a way as well, and it also accounts for high pass term sort of thing actually. So, in general it has negligible effect on steady state performance though. Steady state performance sense it does not matter so much actually, because ultimately the derivative itself becomes 0. If you talk about some sort of the step response happens, then ultimately it happens to be the derivative here is 0 anyway. So, once you compute the derivative in this segment, then it is as good as having nothing actually. Okay. So, that essentially has that property. Now, differentiation of the signal, see what happens actually, differentiating any noisy signal actually amplifies the error quite a bit. That is a terrible effect actually. If there is a noisy signal, suppose I have something, suppose I have a signal which is something like this, and I am talking about taking derivative of that. That means one time I am talking this, one time I am talking that. So, there is a slope of almost positive infinity to negative infinity sort of thing. Okay. So, the noise amplification term becomes quite a lot actually in any derivative part. So, if the differentiation is computed numerically for a particular signal, my strong recommendation is do not use the derivative loop at all. Okay. Whereas the integral loop is okay, because integral is area under the curve. So, any noisy behavior essentially there is a soothing characteristics there actually. Okay. And then if you do the frequency analysis, frequency part of it, essentially you can do that, but it's do the similar analysis. But what it turns out, even the gain margin reduces because of this effect, there is nothing can be, there is a phase margin increase actually. Okay. So, earlier it was both reduction actually, both were in the bad side. Now, it is one in the good side, one in the bad side, but one in the good side. So, nothing can be said precisely, it depends on the problem actually. So, the derivative term, by having a derivative term, whether you are losing robustness, that cannot be told unless you know these values a priori actually, the TD values and all you should know, then you can say that. Okay, the additional requirements for low pass filter, whenever there is a D block in the PID control, you talk about a low pass filter, set point filter, pre filter, etc. actually. Now, you can summarize this, how do you tune up these values? That is the next question actually. Okay. So, how do you tune? There is a summary of table, which you can see that if you increase this Kp, increase this Ki and increase this Kd, what really happens actually. Okay. So, these are rise time, overshoot, settling time, and then steady state error sort of thing. You can nicely have this table handy ready. Okay. For example, if you increase Kp, then the rise time decreases, percentage overshoot increases, settling time is also, I mean, kind of very small change there, and the steady state error decreases. So, that helps us in telling you whether what you should do actually. And similar thing for I and D parts are available actually. Okay. So, then there are that's a manual tuning part. So, no particular math is required, only this qualitative information is kind of good enough, but it requires some sort of experienced personnel for that particular problem, so to come up with a very good tuning basically. Then there are formal approaches available. Okay. There are various things that are available in literature, and they are some of those. One is Kuhn, one is, these are the researchers of names and all that, which is slightly, this particular method is slightly popular in chemical industry for perhaps actually. It results in some sort of an online method of automatic tuning sort of thing, and then however, it is a very aggressive tuning, that means it may upset some inherent advantage of the process as well actually. So, we should not use blindly something actually. There are various ways, people even talk about adaptive PID design, that means the control structure is same, but the gains are adaptive, they change with time based on certain adaptive laws actually. That is a concept of simple adaptive control, which is also available for nonlinear systems as well actually. Okay. There are many things, people interpret that from fuzzy logic rules and all other things actually. Okay. So, that this part I will probably skip, and then limitations of the PID control we should be aware of. These are the that should not skip actually. So, it is a CISO design, primarily single input single output design, and hence can effectively handle only such systems. If there is MIMO system, so you can have a variety of CISO channels, and then it may or may not be sufficient actually. Okay. And systems should behave in a fairly linear manner. If it is a nonlinear system, there is a problem. And then linearity means we should approximately, I mean, use it from in close proximity of some operating point about which we have linearized the system. And obviously, it also does not take into account the limitations of actuators as well. So, there are various concerns in PID control design. It is a wonderful tool, it is a good tool, works in practice, but there are several limitations of that as well. So, techniques to overcome, one popular technique is obviously gain scheduling. Okay, we will talk about little more detail as we go along in this course. Then there are cascading ideas, that means you come up with some sort of a loop structure of control design, like outer loop, command transpose to intermediate loop, then command transfer to inner loop, things like that, and each of the loop we talk about using a PID controller actually. So, that essentially gives us some sort of a cascading thing. Okay. Then filters in the loop and all that actually, those are also available actually. So, you use various filters in the loop as well. So, these are some of the remedies, and that is all I will talk in this particular lecture. Thank you.